This DeBacco University video, I'm going to be going over the types of intermolecular forces, typically abbreviated IMF, often considered to be bonds because of their importance on influencing properties of molecules. All right, so it's important we're going to be looking at intermolecular forces, which are relatively weak, compared to intramolecular forces, which are strong. So in this example, chlorine bound to hydrogen, that bond is an intramolecular force that's very strong. We're going to be focused on the intermolecule to molecule, where we see this due to the electronegativity of chlorine, partial positive, partial negative here. These intermolecular forces are weak, but still have an impact, and we're going to investigate those here. All right, molecular forces are subtle forces of attraction or repulsion between molecules as they play a major role in determining a substance's physical properties, such as its boiling or melting point, also the state of matter considered to be at room temperature. These are a few we're going to kind of go through and discuss. We can see the relative strength here, and a little bit of a diagram here of actually what's going on that molecular level. Let's first talk about the importance of van der Waals forces. These are critical for the consideration of gases, the behavior of nonpolar substances, and interactions in biological membranes here. And we're kind of seeing the positive and negative and the interactions that do occur. This can also occur on that membrane surface as well of cells. It can be really important how different cells are going to interact with one another. Now, those van der Waals forces themselves are temporary dipoles, cause weak attractions between molecules. They're weak and short-lived, but important in large biomolecules. For example, geckos being able to stick to walls is a great example here of van der Waals forces. Maybe that helps you remember this one. There are three subcategories within van der Waals forces: hydrogen bonds, London dispersion, and dipole-dipole. To break those down a little bit more in detail here. We can see some examples, but let's just talk about these and their importance, again, with many things chemically and biologically. So those hydrogen bonds, which you may have heard of before, it's the attraction between a hydrogen atom bonded to a highly electronegative atom like nitrogen, oxygen, or fluorine, and another electronegative atom. Weaker than covalent and ionic bonds, so I don't want you to get the term bonds, yes, it's in there, but they're weaker than the ionic and covalent, but they are critical for biological structures. For example, hydrogen bonds occur between water molecules. Hydrogen bonds also are responsible for holding DNA strands together. How do we represent these? Usually you'll see these dashed lines, and that kind of shows where you have a partial positive, partial negative. Think of it like Velcro. They're kind of like sticking together and breaking, and then they're kind of reforming, and then they're breaking and reforming. But through that moment they're holding together, that is causing an influence on some of the properties. And those properties are looking at, while weaker than ionic and covalent, they are stronger than other intermolecular forces. Hydrogen bonds will increase the boiling point. This is why water has such a high boiling point. At 100 degrees Celsius compared to H2S, which is again just three molecules, negative 60 degrees Celsius. Not many hydrogen bonds occur here. So it takes a long time to boil water because it requires a lot of energy to break all of these little individual hydrogen bonds. Hydrogen bonding is a strong intermolecular interaction between the hydrogen atom and the oxygen of the water. It could also be nitrogen or fluorine, as well as the lone pairs. Now, the importance, as I said, of those hydrogen bonds, typically just abbreviated H bonds, they're critical for biological systems, determining the structure and the function of proteins, nucleic acids, and water's role as a universal solvent. So more than just purely chemical, we're looking at biochemical as well. Now, London dispersion forces are temporary dipoles caused by the random movement of electrons present in all molecules, but dominant in nonpolar ones. So here we see the symmetrical distribution of electrons, instantaneous dipole moment due to the asymmetry, and an induced dipole moment in a second atom. So when these electrons are moving, now we got a positive and a negative end. Now those can cause attractions, and they can shift around, break again, reform. This can happen again and again. Now, those dipole-dipole interactions are attractions between the positive end of one polar molecule and the negative end of another. So again, we're looking at very similar to hydrogen bonds that we see here with the dashed lines. This is technically looking at in more detail a dipole-dipole force. And if we have a positive and negative, they're going to, of course, want to attract to one another. But if we have two positives or two negatives, that's going to cause the opposite. That's going to cause a repulsion, essentially, to occur. Now, a dipole-induced dipole, this is a unique situation where a polar molecule induces a temporary dipole in a nonpolar molecule. So here we've got a polar molecule, induced dipole here of a nonpolar molecule. Because of its strong negative force here, it's pulling and wants to attract to the positive charge, so it's creating a slightly positive and negative end to this oxygen molecule, causing an induced dipole. Without this polar molecule here, this would not occur. So because it comes in close contact with it and it induces this dipole, that's where it gets its name from. Now again, just some other examples here of nitrogen has London dispersion forces allow the N2 to condense into a liquid at very low temperatures. And iodine, or I2, has weak van der Waals forces, contribute to its solid state at room temperature. So again, these small little forces, while they may be weaker than ionic and covalent, they still have a large impact on the properties and therefore the biochemical processes.